All right, guys, so this is the assignment 502.4 Momentum and Kinematics problem set. I'm going to work through these problems starting with number 1. Number 1 says a 0.52 kilogram billiard ball is at rest. An 8 Newton force to the right acts on the billiard ball during a 0.22 second time interval. What is the velocity of the billiard ball at the end of this time interval? And so we have a billiard ball that has a force acting on it to the right. That force is 8 newtons. The mass of my billiard ball is 0.52 kilograms. Its force, I can write it again, but force is 8 newtons. It's in my diagram up there. The time over which that force is acting is 0.22 seconds. The billiard ball is initially at rest, so its initial velocity is 0 meters per second, and then after this force acts on it, it's moving. And that's what it wants us to find, is how fast is it moving after that force acts on it. And so we have this information given to us in the question. When you look at these values, mass, force, time, and if I see VI and VF, of course I have those two separately, but I also know that when I see both of those, that means that I can look at anything that has delta V in the equation. And looking at the equations I have for this unit, the one that I'm going to want to use is F times T equals M times delta V. That was my momentum or impulse momentum theorem. And so I'm going to substitute into this equation. My force is 8, my time is 0.22, the mass is 0.52, and we're trying to solve for delta V, but specifically we're trying to solve for VF. Remember, delta V is final velocity minus initial velocity. So by substitution, I can put this in up here instead, VF minus 0. And so that is my substitution step. Now, of course, if I'm subtracting 0, I can just get rid of that altogether. And let's go ahead and multiply. 8 times 0.22 is 1.76 equals 0.52 VF. From here, I need to isolate this variable, and I need to do that by division because it's currently being multiplied by 0.52. So we're going to divide both sides by 0.52. That isolates my variable, and that goes in my calculator, giving me an answer for my final velocity, VF, equals 3.385. It's actually 3.3846, and the number keeps going. Looks like that. Okay, but I'm going to round it a little bit so that I don't have to write all those digits, and that's also what I'm going to type here for my final velocity at the end of that collision, 3.385. Now, after that initial impulse, after this collision happens, the ball then experiences a constant force of 0.8 newtons to the left for 1.5 seconds. What is the velocity at the end of the 1.5 seconds? So we no longer have this force, which means we no longer have the time that's applied. We no longer have the same change in velocity or anything like that. We're looking at a different scenario, but it is still involving the same billiard ball. So I do want to use some of the same information. I have the same mass, 0.52 kilograms. Okay, but I'm not going to use the force or the time from the first question. In fact, they gave me a new force and a new time. Okay, so maybe this is a situation where you hit the billiard ball to get it moving, and now there's this force opposing its motion to the left. Maybe it's friction being applied for 1.5 seconds, and it wants to know how fast it's going at the end of that time period. So again, it does tell us a new force. It is to the left, so I want to label it as negative 0.8 newtons. The time that this is being applied is 1.5 seconds. The final velocity we're looking for, is what we're looking for, but there's one other piece of information that I know. I also know the initial velocity. Okay, and I know that because this ball is moving now, and it's moving because of this. So it's initially hit or struck, whatever, pushed with some amount of force. This force initially got it moving because at the end of this time, it's moving. And so my initial velocity here isn't 0. My initial velocity here is the answer from my previous question. It was moving after that first impulse, it's moving 3.385 meters per second. That answer that I had at the end of the collision is now my initial velocity as it's rolling to a stop or slowing down, whatever's happening. I don't actually know if it stops. We're going to figure that out by finding the final velocity. But if you look, it's the same information I knew in the last question. Mass, force, time, change in velocity. So it's the exact same equation that I used in the last question. F times T equals M times delta V. My force this time, negative 0.8. My time this time, 1.5, equals 0.52. That's my mass. And again, change in velocity is VF minus VI. VF is what I'm looking for. VI is 3.385 in this problem. And so from here, I'm going to multiply negative 0.8 times 1.5 to get negative 1.2 equals 0.52 VF. I'm going to actually distribute this. Okay, and then minus, because it's minus right here, so 0.52 times my 3.385. I'm going to use the value that hasn't been rounded though, minus 1.76. Okay, so again, I distributed that, and when I multiplied it by that value that I had here, that 0.52 times this value here, I got that, and of course I'm subtracting it. Okay, so from here, again, I'm ultimately trying to solve for VF, so I need to isolate that variable. My next step mathematically is to add 1.76 to both sides. Again, you can't subtract this. These are not like terms. Okay, so you have to get this out of here, and we're going to do that by addition. So it's going to be 1.76 minus 1.2, which gives me 0.56 equals 0.52 VF. From here, to get this by itself, we're going to divide both sides by 0.52. And that gives us a final velocity of 1.077 meters per second. And again, that's a little bit rounded. This is the way that it appears in the calculator. But let's go ahead and type it into our answer, 1.077. So again, for this question, it's really important that you keep your information straight. Make sure that you're not using the force and the time from part 1 and part 2 because it's a different force and it's a different time. And then do make sure that you take that velocity that happens at the end of that impulse and that you know now that that's how fast it's moving at the start of this section. Okay, if you need to see another example of this question or one like it with similar numbers, there is a link down here at the bottom with a video clip worked out with a similar question to this one. Number 2 is probably the trickiest question in this entire assignment. It says a 67 kilogram diver drops from rest on a diving board 2.9 meters above the surface of the water and comes to rest 0.64 seconds after reaching the water. What is the magnitude of the force the water exerts on her? And what makes this difficult is you guys are reading this question and you're seeing, oh, her initial velocity is 0, and then you're looking at this and saying her final velocity is 0. And you can't do that because there's a lot of stuff happening in between here. In fact, there are 2 different portions of this problem. You have to look at exactly what's happening. So it might help if we draw a picture. Okay, and so here's my diving board. This is 2.9 meters. Okay, and so I know that my diver is going to start up here, and that diver is going to fall until they reach the surface of the water. And this entire portion is going to be free fall. Okay, I'm going to have acceleration due to gravity and a free fall situation, and when they hit the water, they're moving. Yes, they will come to rest after they hit it, and that's the second part, is now you have an impact or a collision with the water. Okay, and that collision, that's where your final velocity is 0. Your final velocity of this part's not 0. You need to figure out how fast you're going here so that you know your change in velocity when you have this impact, this collision. Okay, so there are 2 parts to this question, and if you have a question with 2 parts, Okay, like the last one had 2 parts as well. We want to go ahead and separate and make 2 lists of givens. I'm going to list my givens for what I know about the free fall section, and then on a separate little column here, I'm going to list what I know about the collision. It's the same diver in both cases, so I can use the same mass, 69 kilograms, 69 kilograms. Okay, I know that for the free fall portion that they start at rest, but here I'm not starting at rest. I'm moving. After you fall, you're moving. Right before she hits the water, depending on how far she fell, she might be moving pretty fast. Okay, so my initial velocity here is not 0, but my final velocity here is. And I know that because that's what it says. Comes to rest 0.64 seconds after reaching the water, which is the next thing. That time, that 0.64 seconds, that's the time of the collision. And some of you are trying to use that time for the free fall. That is not the time she's in the air. It doesn't say she falls for 0.64 seconds. It doesn't say she's in the air for 0.64 seconds. It says that that's how long it takes her to stop when she hits the water. That time is for the collision, not the free fall section. If you're missing this question, it's probably because of that issue. Okay, you have to filter through the information and you have to label it appropriately. I don't actually know the time that she's in the air. It's not given to me in the question. Okay, let's look at what other information is given to me. I do know her displacement when she's in free fall because I know that she started 2.9 meters above the water, which means that she fell 2.9 meters and her displacement is therefore negative 2.9 meters. Okay, I didn't write that very neat, but it's negative 2.9 meters is her displacement. That's how far she falls when she gets here. Okay, that appears to be the only information that's given to me in the question. However, I know that if I have something in free fall, that my acceleration is due to gravity and it's negative 9.8 meters per second squared. And so this is the information I know about the diver for the free fall portion. And what I really need to find is how fast she's going here, because if I know that final velocity here, that's also how fast she's moving here. And if I can figure out how fast she's moving, I can get her change in velocity and then I can solve for her force. Okay, so we're going to solve for that final velocity. And again, maybe you didn't see that right away. Maybe you want to find time first. Go right ahead. Figure out how long she's in the air. You don't need it, but you can use it if you want to find VF. Find anything you can. Okay, and so using this information here, I can refer back to my kinematic equations, which don't contain mass, and that's okay. Okay, but I can refer back to my kinematic equations, and I can solve for the final velocity that the diver has upon hitting the water. Using my kinematic equations and this information, the formula that I could use to solve this in a single step is this one, VF squared equals VI squared plus 2 times A times delta X. So that's what we're going to substitute into. VF squared equals VI squared is 0 squared plus 2 times negative 9.8 times negative 2.9. Again, 0 squared is going to be 0, but let's go ahead and multiply these out. 2 times 9.8 times 2.9. Again, those negatives are going to cancel each other out. And I get this. VF squared equals 56.84. Again, that's not my final velocity. I need to take the square root to get VF. And the square root of 56.84 gives me a final velocity of plus or minus. Don't forget, when you take the square root of a number, your answer is technically plus or minus 7.539. meters per second. That would be the final velocity at the end of that fall, just before she hits the water. Now, it can't be plus or minus, it's one or the other. In this particular situation, she is falling downward, and so we're going to say that her final velocity is negative 7.539 meters per second because she's falling in the negative direction. And so that's the final velocity. That's not the answer to this question, but it is information I can use here. because her speed at the end of her fall is how fast she's moving initially upon hitting the water. So my final velocity here is my initial velocity here, and it's negative 7.539 meters per second. So now I have an initial velocity, a final velocity, a mass, and a time, and I am trying to find force. That's what the question asks for. What is the magnitude of the force the water exerts on her? And so we're going to set this up using the same equation I did in the last problem for number 1. Ft equals m delta v, because look, force, time, mass, again, Vf, Vi, that's delta v. So let's go ahead and plug in. Force times my time is 0.64 equals the mass is 69, and my change in velocity is Vf minus Vi, which is 0 minus negative 7.539. And again, if I am doing 0 minus negative number, it's really just 7.539. Okay, so let's go ahead and solve this. So we're going to take that number and multiply it by her mass, 69, and that gives us this, 0.64 F equals 520.207. Okay, and again, I'm trying to solve for force, so let's divide both sides by 0.64. Okay, and that'll give me the time. So we're going to take my answer and divide it by 0.64, and that gives us this is our force. And it wants the magnitude, so if it was a negative number, which it's not, but if it was, I would drop that negative sign. 812.82. And guys, I didn't round any of these values as I used one for the next. I know I said them rounded, I know I wrote them rounded. I didn't write all the digits. But when I actually go to solve, I did not round at these steps. I used the whole value. If you round at the intermediate steps, you may have rounding error at the end, and my open math is going to count that wrong. So please be careful and don't round until the very end when you type in your answer. Again, if you need to look at a similar question, look at this link down here. There is a video down here that is going to go over a similar problem with similar numbers. But guys, in this particular one, the most important thing that you need to make sure that you do is recognize that there are two different things happening here. She falls and then collides. And the acceleration when she falls, negative 9.8, not the same acceleration here. The time when she falls, not the same time here. Okay, there are some things you can use, like this velocity at the end is the initial velocity here. Her mass doesn't change. But the rest of these values, you have to make sure that you label them correctly, whether it's for the free fall or for the collision. All right, question number 3. Question number 3 says, in 1,840 kilogram car, so let's start by labeling the information, 1840 kilograms, traveling to the west slows down uniformly from an initial velocity of 24.3 meters per second to a final velocity of 17 meters per second. How long does it take the car to accelerate as described if the force on the car is 2686 newtons to the east? Okay, so there are some directions in here, and our car is going to the west, but our acceleration is to the east. Okay, and whenever you have things happening in opposite directions, you need to make sure your signs are opposite. Now, you're welcome to call the west negative, or you're welcome to call the east negative. Okay, it doesn't matter. We're going to get the same answer here for the time regardless. I'm going to go ahead and say that my car is traveling forward, and I'm going to say west is forward, and therefore this force that's going east, that's going opposite, I'm going to call a negative number. So my force is going to be negative 2686. Okay, and I've just defined east as the negative direction by doing that. Okay, with this, I now have mass, 2 velocities, which means I can find delta V, and force, and they want me to find time, and again, it's the same equation we used for the first 2 problems. F times T equals mass times delta V. We're looking for time. So that negative 2686 times the time equals the mass, 1840, times the change in velocity. And again, change in velocity is Vf minus Vi, which is 17 minus 24.3. So from here, let's go ahead and subtract 17 minus 24.3. And we get negative 7.3 for that. And we're going to go ahead and multiply that by 1840. Okay, so this negative 13,432 is equal to negative 2686t. And again, we're trying to solve for time. So we want to get it by itself, which means we need to divide both sides by negative 2,686. So we're going to take that number that's in my calculator already, and I'm going to divide it by my force, negative 2686. And that's going to give me a time of 5.001 seconds. Okay, so that's going to be your answer to the first one. You actually don't need that third decimal. It only requires 2 in my open math. So I'm just going to type 5.00. The next question says, how far does the car travel during the acceleration that occurs as it slows down? So this time we're looking for delta x. How far does it go as these things are happening? And this is a continuation of the same problem. It's not talking about a different force or something else happening. It's all part of the same thing right now. So that means we get to use all this information to help us with this. Oops, just seconds. Okay, so if I want to find delta x, that means I need to be thinking about my kinematic equations. And my kinematic equations have VF, VI, time, delta x, and acceleration. And I have one that I can use to find delta x without acceleration, because I don't have that right now. Now, could I find it? Sure. It'd be pretty easy to do. You're welcome to do that. Or you can just solve for it like this. Delta x equals VF plus VI divided by 2 times t. There's no acceleration in that equation, so I can do this all in a single step. So that delta x will equal 24.3 plus 17 divided by 2 times that time of 5. Okay, so let's do this. 24.3 plus 17 divided by 2 times my time. And it wasn't exactly 5, it was this value up here, almost 5. Okay, but I get this, 103.265 or 103.27 if I round it. All right, the next part again says, assuming the car experiences the same force and acceleration as above, how long would it take to reach a complete stop? So again, still a continuation of the same problem, but we're not going to use this delta x we just found. We're going to actually look and see how long it would take to go all the way to 0 instead of just to 17. For the third question.
Hello. Do you have an...
Okay, so in this problem, we know that the initial velocity, and they restated it for us, is 24.3 meters per second. Here we're looking how long it takes to stop, so the final velocity we need to use here is 0. And again, it has the same force and acceleration. And so that force that we used previously, we're still going to use it here, negative 2,686 newtons. We didn't actually find the acceleration up here, so we don't have that value that we can use. But we could find it if we needed to, because we also know the mass is 1,840 kilograms. So you could determine the acceleration using F net equals ma if you wanted to know what the acceleration was. And of course, because these values are the same, you'd have the same acceleration here. So we're trying to determine the time that it takes the car to reach a complete stop. And again, we have two velocities, so we have change in velocity, force, mass, and time. So we're going to go back to this equation, F times t equals m times delta v. Again, alternatively, as I mentioned a moment ago, you could use this information to solve for acceleration using F net equals ma. And once you have acceleration, now you have opened up the opportunity to use kinematic equations. You have VI, you have VF, you would have A, and you could find T that way as well. So you've got a couple of different options here, but I'm going to go ahead and use our impulse momentum theorem. Substituting in is negative 2686 times T equals our mass, which is 1,840, times our change in velocity. Final minus initial would be 0 minus 24.3, so that's a change of negative 24.3. From here, let's go ahead and multiply 1,840 times negative 24.3, and that gives us this, negative 2686t equals negative 44,712. Again, if I want to solve for this time, I need to isolate that variable, so we're going to divide both sides by 2,686. Again, that's negative 2,686. Those negative signs over here are going to cancel each other out, and so we're going to get a positive number, which is good because we're solving for time. It should be positive. So if I divide my 44,712 by 2,686, we get a time of 16.646, and that's just in seconds. I keep trying to write meters, but 16.646 seconds, or if I want to round that further, 16.65 seconds. The last question says, how far would the car move before stopping completely? So now we have this time, we can determine how far, delta x. Again, if you're solving for how far, if you're solving for your displacement, you automatically should recognize that you need to use kinematic equations. Since I don't have an acceleration up here, again, I could find it and then I have more options, but because I don't currently have that, I can solve for my displacement using this equation, delta x equals vf plus vi divided by 2 times t. And I can get it without ever having to solve for acceleration. So let's go ahead and substitute in that vf is 0 plus vi 24.3 divided by 2 times my time that I just got, 16.646. And that gives me an answer, delta x equals 202.25 meters. And again, let's go ahead and type that in, 202.25. Question number 4. A 2.45 times 10 to the third kilogram car is initially traveling to the right along a level roadway when it applies its brakes and slows down uniformly. The car was initially traveling 25.6 meters per second before applying a braking force acting opposite the car's motion. The coefficient of friction between the tires and the road is 0.36. There's a free body diagram here, and it says a physics student drew the free body diagram above to show the forces acting on the car for his homework. Which statement correctly describes the free body diagram he drew? So it's basically asking whether or not he drew it correctly, and if it's not correct, what's wrong with it, and there's some options here. It says the force of friction should be pointing in the opposite direction. So right now he has force of friction pointing to the right, and based on the information in the question, the car is traveling to the right. Friction does always oppose the motion, so his friction is drawn in the correct direction. That is not an issue for this diagram. The second one says he drew the correct free body diagram, and that's not a correct statement either, because his free body diagram contains an applied force that is not described in the question. In fact, it says that this car is traveling and it starts to slow down. They're applying their brakes. They're no longer applying a force forward. They're not stepping on the gas at the same time. And so there is no forward force. The car is moving forward because it was already moving forward. It's going to come to a stop because of the friction between the road and the tires, or the brake pads and the wheels. And so this is not a correct free body diagram for the situation, so we're definitely not going to select that statement. The next statement says the normal force and gravitational forces should not be equal. In this situation, we have this car on a level roadway, so there's no angle here. It's just traveling along a level roadway, and there's no vertical motion, much less vertical acceleration. And so we definitely don't want these to be different in length. They need to be equal and opposite, and so that statement's not true either, which leaves us with the last statement. The only horizontal force needed is force of friction, thus FA should be removed. And we've already said that that is a true statement, and that's the box I'm going to check. Again, this question is going to be randomized for your particular version of this. So you might have the correct free body diagram. It really just depends on what yours looks like, but you need to read the statement and recognize that the free body diagram should look like the one that I see here, except it should not have an applied force. So the rest of this is actually correct. All right, now we have 3 different questions to answer about this scenario. The first one is, what is the braking force acting on the car? Then what is the car's velocity after 2.39 seconds? How far does it move during that time? And then how long does it take to come to a complete stop from that initial velocity? So we need to go ahead and write down some information from this question. All right, so we know in this question, we know that the mass of this car is 2.45 times 10 to the third, which I'm going to go ahead and put in standard form as 2,450 kilograms. I know that this car is traveling to the right with an initial velocity of 25.6 meters per second. I know that I have this braking force opposite the car's motion. I know that there is a force of friction, but it's not given to me. However, they do provide me with a coefficient of friction of 0.36. Okay, and so I have that information. I do need to find this because that is going to be the net force acting on the car. Because remember, this diagram, I said if we remove FA, it's correct. And so the net force, the only force that's not canceled out, will be force of friction. So that FF will be my net force, and I can use that to find my acceleration or whatever calculation I'm doing. So then that's the first step. What is the braking force acting on the car? I'm going to redraw the free body diagram, except we're going to draw it correctly this time. We have Fn, we have Fg, and we have Ff. Okay, so that's what the diagram is supposed to look like. These should be equal and opposite to each other. And so we're trying to determine what this is. And again, we have a formula to find force of friction. It's equal to mu times Fn. And so I already have mu, I can find Fn. I don't have a formula for Fn, but it is equal to Fg. And so I know that they have the same magnitude, and I do have a formula for Fg. Mass times gravitational acceleration. On Earth, this is 9.8. I know the mass, it was in the question. So I can simply take that 2,450 kilograms and multiply it by 9.8, and I can get the magnitude of Fg and thus Fn as well. So 2,450 times 9.8 gives me not just Fg but also Fn, and that Fn is equal to 24,010. So 24,010 newtons is my normal force, and that number can go into this equation here. Mu times Fn. So I'm going to take that Fn, that 24,010, and I'm going to multiply it by my coefficient of friction, which was 0.36. Again, that number was given to me in the question. And when I multiply them, I get my force of friction. And I'm going to tack a negative sign on. I don't get a negative number in my calculator, but I know it's negative because it's going in this direction. Negative 8,643.6 newtons. So now I have my force of friction, and that is also my braking force. So let's go ahead and type it in. Negative 8,643.6. What is the car's velocity after 2.9 seconds? So they just gave me another piece of information. They've told me, hey, start looking at this particular time window, 2.39 seconds. Okay, and so with this information, we're trying to find how fast it's going at the end of that. Now I have FF, which means I have my net force, and I could find my acceleration, and then I could find VF using kinematic equations, or because I see that net force, and I see mass, and I see time, and I have an initial and a final velocity, well, I'm looking for that final, I have those two labeled, I can use this equation, F times T equals M times delta V. My force is again that negative 8,643.6. My time that they gave me is 2.39. It is equal to, my mass is 2,450, and my change in velocity, again, change in velocity is VF minus VI. I don't know VF. I do know VI. And so that is my setup. Okay, so from here, I'm going to go ahead and multiply these and get this. Negative 20,658.204 equals, this needs to be distributed, so 2450 VF minus 2450 times 25.6, which is 62,720. Okay, so again, I am trying to find this. Need to get that by itself. So my next step is going to be to add 62,720 to both sides. That's going to cancel this, and over here I'm going to get this, 42,061.796 equals 2450 times VF. And again, I'm still not done. I need to get this by itself, so we're going to divide both sides by 2,450. To get that by itself, and we get a final velocity of 17.168 meters per second. So let's go ahead and type that in here. 17.17 if I want to round it. How far does the car move? So now we have a final velocity. We can find delta x. We're going to use the same set of conditions because it says based on the same information. So we get to use all these same values, including the final velocity we just found. And since I don't have an acceleration, that's going to be helpful to me because I do have a formula to find delta x. And again, if you're looking for delta x, it's going to be a kinematic equation. But I can use this one, VF plus VI divided by 2 times t. Or I can go find the acceleration and use a different kinematic equation. But this is the fastest way to do it in one step. So I'm going to take my previous answer, 17.168. I'm going to add to it my initial velocity, which was 25.6. We're going to divide that by 2 to get our average velocity for the time period that is 2.39 seconds long. And that will give us our displacement. So let's go ahead and put this in the calculator. And we get a displacement of 51.108 meters. And again, I'm rounding when I'm writing it down. I have a lot more digits on my calculator screen for all of these numbers, but this is sufficient for me to type it in here. And so I'm going to type in 51.11 to round. The last part of this question is actually telling us, hey, ignore these previous two parts when we talked about the 2.39 seconds, because this is saying how long does it take to come to a complete stop. We're not at a complete stop after that 2.39 seconds. We're still moving that fast. Okay, and so let's go ahead and ignore the two that we just did and go back to the information that we started with. Okay, so that means we still have the mass. It was 2,450 kilograms. We still have the same braking force. That one was negative 8643.6. We still have the same initial velocity. In fact, it tells us again from the initial velocity of 25.6 meters per second. So we still have those values that are the same. Now it's asking us to stop. How long does it take to stop? So our final velocity we're going to use is 0, and we're looking for time. Again, there is more than one way to do this. I could, once again, find that acceleration and then find the time using kinematic equations, or I can do the same thing I've been doing and use this one. F times t equals m times delta v. My force, again, is negative 8,643.6. I'm looking for the time it takes to stop. My mass is 2450, and the change in velocity is final minus initial. If you go from 25.6 to 0, that's a change of negative 25.6. Okay, and so this is what we're going to put in the calculator. So we're going to start by multiplying 2,450 times that negative 25.6, and that's going to give us negative 62,720. Okay, equals negative 8,643.6 t. From here, I want to solve for that time, so let's go ahead and divide both sides by that negative 8,643.6. That isolates my variable. Those negatives cancel, and we get a time of 7.256 seconds. Again, the time we get here should be longer than the time in the previous question. Okay, that 2.39, and it is because it was still moving here. So it should take longer than that to actually come to a stop. So you can make sure your answer makes sense. It does. 7.26 is an appropriate way to round that number to 2 decimal places. Question number 5 is somewhat similar to the one we just looked at. It says, 2 brothers ride a sled in the snow. The combined mass of the boys on the sled is 194 kilograms. The sled slides rightward for 9.2 seconds across the surface of a frozen lake until it comes to a stop. The coefficient of kinetic friction between the sled and the ice is 0.079. And again, it says, hey, here's a free body diagram. What's wrong with it? Okay, and so we have this sled sliding rightward until it stops due to friction. So again, just like the last one I had, I shouldn't have an applied force here. Okay, there's nothing in here that says that they're pushing it forward. There's no continual force applied. It's simply moving in that direction already. And so whenever I look at this, I want to select the option that says the only horizontal force needed is FF, thus FA should be removed from this free body diagram. I don't know if there's anything else here because there might be more than one statement, so let's check. This isn't correct. Force of friction should be the opposite direction. No, it says the sled's going to the right. Friction needs to be opposite that. So we're good there, so we don't want to select that. That's not going to be correct. Nope. Okay, so the only thing we should be selecting is this first one that's on my screen. And again, we have some calculations to do based on the information we were given in this question. So let's go back up and label what we know. We know that the mass of this system of the boys and the sled is 194 kilograms. We know that the time that it's moving is 9.2 seconds. We know that the final velocity of the sled is 0 meters per second. We know the coefficient of friction between the sled and the ice is 0.079. And we know that the free body diagram should look like this instead of what was on my screen. Okay, so that's the information that I see in the question. So the first question says, what is the change in the sled's momentum as it comes to a stop? Okay, well, when it comes to a stop, the momentum of the sled is going to be 0. So the change in the sled's momentum, if I found the initial momentum, then I could answer this question. However, I don't actually have an initial velocity, so I can't do that. But change in momentum is also equal to mass times change in velocity, or to force times time. I do have a time, and I have a free body diagram here with some forces on it. The net force is going to be my force of friction. So if I can figure out what my force of friction is, I can multiply it by my time, and I can then be looking at this equation. Impulse equals change in momentum, which equals force times time. So again, this is how I'm going to figure out the change in momentum. Because it's equal to impulse, it's also equal to force times time. So I need to get that force. Again, force of friction, I have a formula for that. It is mu times Fn. Okay, I have mu, 0.079. I just need Fn, and I don't have an equation for Fn, but I did mark down that it is equal and opposite to Fg, and I do have an equation for Fg. So, if I solve for Fg, my mass, 194, times gravity on Earth, 9.8, I get an Fn of 1901.2, and that's also Fg, so they're both the same value, 1901.2 newtons. Now I can multiply that by my coefficient of friction, so 0.079 times 1901.2, and that will give me my force of friction, Ff, which is equal to negative 150.1948 newtons. Okay, and I listed it as negative because I know it's going in this direction. So that will help me now to answer the question. This is not what the question asked. I need to tell what the change in momentum is. But again, change in momentum is equal to impulse, and impulse is equal to F times t. Here's my net force, here's my time. So if I want to solve this problem, I can say my change in momentum is equal to my force, negative 150.1948, times my time, 9.2. Okay, so let's go ahead and multiply our answer from the previous one times the time, 9.2 seconds, and we get a change in momentum of negative 1,381.79, and I'm rounding that a little bit, kilogram meters per second. So, change in momentum, negative 1381.79. What is the sled's initial velocity? Okay, well again, I have now the change in momentum. I know that my final momentum is 0, so I know that my initial momentum would have been positive 1,381.79, and I can use that to solve for my initial velocity. Okay, alternatively, I know that change in momentum, delta P, equals mass times change in velocity, and it's effectively going to do the same thing if I go about it this way. I just need to substitute in here that delta P equals mass times VF minus VI, okay, because that is delta V. And so if I want to substitute in, I have negative 1,381.79 equals my mass, 194, times VF is 0 minus VI. Okay, of course that 0 goes away, and I have negative 1381.79 equals 194 times negative VI becomes negative 194 VI, and now I can divide both sides by negative 194. To get my initial velocity, those negatives are going to cancel, and I get an initial velocity of 7.12264 meters per second. Okay, and that's actually all the digits. I didn't round this one at all. And so that would be the sled's initial velocity. Let's go ahead and type that. 7.12 will be sufficient. We don't need to type all the decimals. All right, the next question says, how far does the sled slide? And again, as I mentioned already, if you see a question about how far, delta x, you need to use kinematic equations. I don't have the acceleration calculated. I could very easily find it because I have my net force and I have my mass. I could do F net equals ma to get it and then find this. Or I can use the kinematic equation that I know that allows me to solve for delta x without using acceleration. And that's this one. Delta x equals VF plus VI divided by 2 times t. Again, I'm looking for delta x. My VF is 0. My VI is the number I just found, 7.12264. Divide that by 2 and multiply it by my time that was in the question was 9.2 seconds. Okay, so we're going to take our 7.12264 and divide it by 2, and then multiply our answer by 9.2. And we're going to get from that a displacement delta x of 32.764 meters. And again, that is rounded a little bit because there's all the digits. But how far does it slide? Question number 6. At 25 meters per second, the braking distance of a typical car of mass 1,670 kilograms is about 78 meters. Calculate the braking force for a typical car. All right, so initial velocity, 25 meters per second. We're talking about a car braking from this speed. Braking implies that we are stopping. Final velocity, 0. The mass is 1,670 kilograms. The delta x is 78 meters, and we're trying to solve for force. Okay, so in order for me to solve for force, looking at this, I know that I see VI, VF, M, and F, and so I know that I have this equation, F times T equals M times delta V. However, I know that I can't use it because I don't currently have time. And so a good first step would be for me to figure out the time of this. And I know that I can find time not just in that equation but also in my kinematic equations. I've got 4 of them. Those kinematic equations contain variables of VI, VF, time, T, A, and delta x. And looking at my paper, I have 3 of those. That is enough for me to find time. So I'm going to use this kinematic equation, delta x equals VF plus VI divided by 2 times time. I'm going to use it to find the time and then plug it in here and I can find my force. So I have my 78 meters. My VF is 0, my VI is 25 divided by 2 times T. So 25 divided by 2, let's go ahead and work that out. 78 equals 12.5 T. And now we just need to get this by itself. Divide both sides by 12.5. That cancels, that isolates T, and that goes in my calculator. 78 divided by 12.5 gives me a time, T, of 6.24 seconds. Okay, again, this was the first step in answering the question we're being asked because now I have time, I have a change in velocity, I have mass, I can find force, and I'm going to go back up to this equation. So let's go ahead and use that. F times my time that I just found, 6.24, equals my mass, 1,670 times my delta V, that's VF, 0 minus VI, 0 minus 25, of course, is negative 25. Okay, and so from here we're going to multiply 1,670 times negative 25, and we're going to get negative 41,750, which is equal to 6.24 F. Again, we want to get F by itself, so we're going to divide both sides by 6.24. When I do that, I get that my force is equal to negative 6,690.7051 newtons. So that would be my braking force, and it should be a negative number because it is causing us to slow down. 6690.71. Question number 7 says a baseball player with a mass of 93 kilograms slides for 0.84 seconds as he slides into home plate, where his final velocity is 0. The coefficient of friction between the player and the dirt is 0.486. So let's go ahead and label what we know. We know the mass is 93. We know the time of the slide is 0.84 seconds. We know the final velocity at the end of that slide is 0 meters per second. We know the coefficient of friction between the player and the dirt is 0.486. And that's the information in the question. Okay, so which describes the free body diagram below? Okay, this free body diagram would either show a baseball player at rest or a baseball player moving at constant velocity, but that's obviously not the case because this player is sliding until he stops. So this is not what I should see for somebody sliding. Okay, the only horizontal force needed is FF, thus FA should be removed. That is correct. Once you're sliding, you're no longer applying a forward force. You are just moving with the momentum that you had. You're an object in motion. You're going to continue moving until something acts on you, and there is something acting on you the whole time. That's friction that's going to cause you to accelerate until you stop. And so our free body diagram for this should look like this. Just like the last couple that we've seen. Okay, let's see. Nope, okay, so we're good with the rest of the statements. We only need to select that one. And we have some questions to answer here. The first of which says, what is the player's change in momentum? So we're looking for delta P. The second one, what is his initial velocity? That's VI. And the third one, how far? Delta X. So change in momentum, again, if I know that his final momentum is 0, I could get his initial momentum and of course find the change that way. Initial or final momentum minus initial momentum would give me change, but I don't have the information about his initial velocity. So the other thing I can do is that I know delta P is equal to impulse. Okay, so it's not just equal to mass times change in velocity, it's also equal to force times time. And I have a time, and I have some forces in my diagram. So if I can figure out my force of friction, because that is my net force, these cancel, this is the only force horizontally. If I can figure out my force of friction, I can multiply it by my time, and that will give me my impulse, which is equal to my change in momentum. So my task is to find FF. My equation for FF is mu times Fn. I have mu right here, 0.486. Fn, don't have a formula for, but I know it's equal and opposite to Fg, and Fg is mg. So I'm going to take the player's mass, 93 kilograms, and I'm going to multiply it by 9.8, mass times gravity. And I'm going to get a weight, an Fg of 911.4 newtons. And again, Fn's equal and opposite to it, so this is also 911.4 newtons. So now I know my normal force. I can multiply it by my coefficient of friction. So I'm going to take that 911.4 and I'm going to multiply it by 0.486, and that's going to give me my force of friction. My force of friction is equal to, and again it's in the negative direction, but negative 442.94 newtons. Okay, so that's my force of friction. Again, my impulse and thus my change in momentum is equal to that force times my time. My time is 0.84, so we're just going to multiply it by 0.84, and we're going to get a change in momentum of negative 372.069936 kilogram meters per second. Okay, and that's actually all the digits right there. I don't have the negative sign on it because I didn't type it in on my friction, but it should be negative 372.07 if I round it. And again, that's because he's coming to a stop, so his change is a -1. He was moving, now he's not. He lost his momentum. What is his initial velocity? Again, in addition to impulse being force times time, it's also mass times change in velocity. And so I can take this answer that I got from my impulse, negative 372.07, and I can set it equal to mass times change in velocity. My mass is 93. And again, delta V, change in velocity, is VF, which is 0, minus VI. So now we can solve for our initial velocity this way. Again, this is delta P equals m times delta V. That's the formula that I'm using. Okay, so again, this 0 is going to go away. And so we have negative 372.07 equals 92 times negative VI is negative 93 times VI. And now we're going to divide both sides by negative 93. That gives me VI. My negatives here cancel, so it's just 372.07 divided by 93. And again, that gives me an initial velocity, VI, of 4.00 meters per second. And again, I did round, but it's 0.00752. So our initial velocity, 4. How far does the player slide? Okay, so let's go ahead and determine delta x. Again, if you see delta x, if you see how far, you should recognize that you're going to be using kinematic equations. Since I have VF, VI, and T, and I want delta x, I'm going to go ahead and use this equation. Delta x equals VF plus VI divided by 2 times T. Okay, and that means that it's equal to 0 plus 4 divided by 2 times the time, 0.84. 4 divided by 2, of course, is 2. 2 times 0.84 is 1.68. Question number 8, and the last question in this assignment says, 2 carts are pushed apart by an expanding spring as shown in the diagram below. Which cart experiences greater force? Which cart experiences greater acceleration? Okay, so forces. This, guys, is a force pair. Okay, the force on each car has to be equal and opposite to each other because it's the same interaction, it's the same spring, it's going to push them both with the same force, which means the answer has to either be B or C. Okay, the question is which one has greater acceleration. So we know the forces are the same, but are the accelerations the same as well? And the answer to that, if they had the same mass, would be yes, but they don't have the same mass. If you apply equal forces to one object that is very light and another object that's heavy, and I asked you which would accelerate more, you know that smaller object accelerates more. The 1 kilogram object would have greater acceleration than the 2 kilogram one because it has less mass. So although the forces are equal, the accelerations are not. We're going to select answer C. The next one says, which experiences greater impulse? Again, this is the same force. The time is the same. It's impossible for it to be anything but the same amount of time because it's impossible for them to be experiencing a force without the other one experiencing it at the same time. So my impulses are equal because I have equal forces and equal times. I'm going to say that, and that's what this says. The 2 carts have equal impulse because both experience equal force for equal time. Which equation or equations appropriately describe this scenario? This first one says that the change in momentum of the 1 kilogram cart is less than the change in momentum of the 2 kilogram cart. Guys, we just said that the impulse was equal. Change in momentum and impulse are the same thing. Mathematically, they're the same. So I can't pick this here and pick this here because those contradict each other. In fact, here's my answer, at least one of them, there could be more than one here, is that they have equal changes in momenta because they have equal impulses, because they have the same force and the same time. Okay, so I'm going to say that the change in momentum of the 1 kilogram cart equals the change in momentum of the 2 kilogram cart. If I look at the options for impulse, that's not an option. There's my statements regarding impulse, so I can't pick any of those. Okay, let's look at these other 2 statements. Mass times change in velocity is the equation for change in momentum. So if the changes in momenta are equal, then that means the mass times change in velocity for each cart has to be equal as well. So I'm going to select both of these 2 options. Okay, and then it says, last question, if the 1 kilogram cart moves away from the collision with a speed of 2.4 meters per second, what is the speed of the other cart as they separate? And guys, we're going to use this equation right here because this is going to help us to see what happens. Both of these carts are initially at rest, and so both of them have an initial velocity of 0. Okay, so if I look at my formula, mass times change in velocity, so I'm going to use this, m delta v equals m delta v. Okay, that's my change in momentum equals my change in momentum for my 1 kilogram versus my 2 kilogram. Okay, so my mass here is 1. The change in velocity here, it says that the 1 kilogram cart moves away with this speed. Well, it was initially at rest. So its change in velocity is 2.4 because now it's moving 2.4. It went from 0 to that. So that is the change, equals this mass is 2 times its change in velocity. And again, change in velocity is VF minus VI, and we know the initial was 0. So you could also write this as, well, 1 times 2.4 is 2.4, so 2.4 equals 2 times VF minus 0, or 2 VF. If I want to solve for VF, let's just divide by 2. 2.4 divided by 2 gives me a final velocity of 1.2 meters per second. And wouldn't you look at that? It is half as fast. This 1 kilogram cart's moving 2.4. The 2 kilogram cart is moving 1.2. It's half as fast. And again, we already knew that. We talked about that up here when we talked about the accelerations. We know that they don't have the same acceleration. That 1 kilogram cart has twice as much acceleration because it has half the mass. So not surprisingly, it's moving twice as fast as this one. All right, guys, that is it for the questions in 502.4. Hopefully you found this helpful. If not, please come in for tutorials.